Hello, this is Senior Design Project Team 13, Mechanical Inerter for Seismic Protection. My name is Scott, and my peers are Joe, Will, Cooper, Nathan, and Eric. The aim of this presentation is to provide an overview of our design, prototype, analysis and experimentation methods, and results. The current seismic damping technology is expensive to implement and maintain while also being failure prone. Think of large tune mass dampers in the middle of a skyscraper or base isolators that act as suspension between the foundation of a building and the ground. Borrowed from Formula One suspension racing technology, the mechanical inerter provides a novel solution to damping vibrations that is relatively small, easily tunable, and easily implemented throughout the foundation of a structure. The goal of our project was to design a mechanical inerter, an experimental setup, and then determine the damping capabilities of the mechanical inerter. The objectives we set forth to meet are damping vibrations with a target value of greater than 50% in the reduction in the amplitude of oscillation. We achieve this value at 56% reduction. Number 2 is a scalable design. With a target value of 1,000 cubic centimeters for the prototype volume, we achieve this value with 783.75 cubic centimeters. Number 3, an affordable design. With a target value for the price of less than $100, and we achieve this value with a price of $64.47. Number 4 was to design a shake table and with a target value of an operating frequency of between 0 and 2 hertz. We achieve this value at 0.88 hertz. And number 5, to create an accurate analytical model with a target value for the R-squared value of 0.9. This value measures the variance in experimental data relative to the analytical model. We did not achieve this value with our value being 0.87 for the R-squared value.
A mathematical model of the mechanical inerter and shake table is a single system that was created to verify experimental results and to easily analyze the inerter's response to varying inputs. More specifically, we used it to determine which spring and flywheel constants most effectively dampen input vibrations, and we use this to influence our final design decisions. The simplified model of the system is shown right here. The mechanical inerter is a cylinder of mass mc. The shake table is this cart of mass mb. Relative motion between the two is created with spring and friction. Friction is assumed to be viscous, nonlinearities are omitted, and the input into the system is velocity v of t, which is a sinusoidal velocity. So the system is second order, and the system of equations shown right here. The states are x, which is the relative displacement of the mechanical inerter with respect to the shake table, and p, which is the relative momentum of the mechanical inerter with respect to the shake table. And then the output of interest, xc/g, is the displacement of the mechanical inerter with respect to ground, which is simply the integral of the velocity input plus x. And the list of parameters used in the final design is shown in this middle table.
We chose a rack and pinion design for our mechanical inerter. Central to our design is a bottomless cart that houses the inerter. Mounted to the cart is a shaft that aligns the large pinion gear and heavy flywheel. The large gear mates with the groove drag. As an input to our design, we built our own shake table. The shake table is driven by a single DC motor and crank linkage. The moving base of the shake table is constrained by CNC rails. The input range of the table is around 6 centimeters. For testing purposes, the inerter is placed atop the moving base.
Using the data obtained from the shake table testing, as well as the analytical model discussed earlier, we were able to obtain meaningful results from these experiments. The plot on the top right shows the simulated position of the mechanical inerter according to the analytical model on the y-axis, with the experimental position of the mechanical inerter according to the shake table testing on the x-axis. The R-squared value for these data points is 0.87, meaning that the analytical model is a relatively good fit, but has room for improvement. Another trend we noticed is that as the spring constant increased, the fit worsened. The table on the bottom left shows that as the spring constant, or spring stiffness, increased, the vibration damping percentage also increased, which was to be expected. The plot on the bottom right shows the experimental response for a spring stiffness of 186 newtons per meter for both the shake table and the mechanical inerter. The shake table displacement over time is shown in blue, and the mechanical inerter displacement over time is shown in orange. Note that there is a slight lag in the mechanical inerter response, but that it is 56% smaller than the shake table response, meaning it reacted as was to be expected.
So the conclusion of our project is that we were able to make an effective mechanical inerter. We were able to reduce input vibrations by 56%. That was with a spring coefficient of 186 newtons per meter. There was a little bit of discrepancy between our analytical model and our experimental tests. This was mostly due to our neglecting of the nonlinear effects in the system. This will require a little bit more work to flesh those out and get a more complete analytical model. In the future, teams are going to hopefully focus a lot on the scalability of this device. We've shown that we can make an effective inerter, and we're hoping the future teams are able to focus more on the scalability, meaning something that's modular, something that can be mass produced, and something that can be integrated into a building easily. And hopefully those future groups will be able to use the shake table that we've created to test their devices and make something that's effective.
Here is the final assembled prototype of the shake table and mechanical inerter-based damping system. For the shake table, we have our linear actuator comprised of the DC motor and this 4-bar linkage connected to the shake table. The shake table itself is outfitted with 3 IR sensors. The outside IR sensors measure the displacement between the shake table itself and ground, which is represented by these 2 walls. The third sensor here measures the displacement between the shake table and the inerter itself. The circuit is mounted to the shake table, which allows for minimum movement of the wires connecting the sensors to the microcontroller. This reduces the noise present in the final signal. All of this is powered by a 12-volt DC power supply. This top circuit here will regulate that 12 volts down to 5 volts to be able to power all of our sensors, as well as the motor is powered by the 12-volt signal as well. For the damping system itself, it is comprised of the inerter component here, which is made up of this rack and pinion connected to this flywheel. Further damping is achieved with the addition of springs. The entire setup is connected via this USB to a computer where a Python script will initiate the test, collect the data, and process it so we can take the raw signal data from the sensors and turn it into the displacement between the shake table and ground and the shake table and the inerter.